Hello everyone. Today we'll be discussing about our survey paper on RTOS memory protection. I am Moshrefa Sultana Chaity and I have my partner Helaluddin with me. Today we will be discussing about the motivation of our work, the research problem, the objective of our work, what is RTOS and memory protection, some related works about this area, conclusion, and finally the references. In modern days, almost all safety critical systems employ a real-time operating system that we call RTOS to execute numerous embedded operations effectively. Memory is always considered the vital component of all software developers, and it is very important to prevent memory crashing in today's real-time based systems. Otherwise, the whole system will fail. Memory protection prohibits one task from overwriting another's memory space. Reduce the disk of corrupted memory, triggering the program failure. The research problem is that the memory protection functionality of real-time operating system is lacking in basic system design. Memory protection system can ensure that the system can be protected from the intrusion. In our paper, we have discussed the literature review of different memory protection mechanisms in real-time operating system. First, we will discuss what is RTOS. A real-time operating system, generally known as an RTOS. This is a software component that switches quickly between tasks, giving the impression that multiple programs are operating on a single processing core at the same time. In reality, the processing core can only execute one program at any time. And what the RTOS does is switch between individual programming threads or tasks instantly to give the impression that multiple programs run concurrently. An RTOS differs in that it usually provides a hard response in real time, providing a fast, highly deterministic response to external events. Therefore, as multiple tasks operate parallelly in RTOS, they will intervene in the memory area of each other and corrupt someone else's data, and as a consequence, the running application can be crashed. Some of the microprocessors available for embedded systems have an optional memory protection unit or MPU, and in some cases, a memory management unit that can be called as MMU to help manage separate memory spaces. This technical note explains the use of an RTOS when implementing a hardware MPU or MMU to protect a memory. What is memory protection unit? The MPU is used to separate different memory regions, meaning that data from one area cannot overwrite or delete it from another. Within the memory map, the MPU can detect access to unauthorized areas. Memory partitioning and the use of it by tasks must either be managed by an RTOS on behalf of the application or by the application directly. An RTOS with native MPU support provides an API and the tools needed to split the application into tasks or threads and handles communication between tasks and the queues or events. The use of an RTOS that provides the MPU with native support makes for more opportunities to enforce partitioning at a fundamental level. This makes it much easier for the application to ensure integrity and obtain certification to a high safety integrity level. This is an image of separating an application into multiple processes. And memory management unit serves the same function as the MPU does in memory protection. But it also provides more sophisticated memory control functionality required in complex systems. For memory protection, we will first discuss about the hardware support. Memory protection has undergone evolutionary processes with hardware support. It is entirely enforced by software during early years of system protection without any hardware support. Hardware support has been granted greater emphasis and value since mid-1960s. Hardware approach initially applies to adding certain easy to implement instructions to a series of standard computer instructions. These instructions are used to transfer in the function registers from the functional segment. Later, because the computer has a relatively large microprogram memory, new design is introduced as the OS design would include the security kernel. Although all security related features are concentrated in the kernel, it can choose to construct part of the kernel in order to allow the rest of the operating system for the same protection mechanism as the security kernel. Many parts of the security kernel require the access permissions. Now we will discuss about memory protection in tiny embedded processors. Memory protection is typically accomplished by co-designing the software or hardware. This approach eliminates the risk of extensions to architecture. Generally, the system is designed primarily in software, where the memory map can be splitted into three parts as protection regions, data structure, and memory map checker. The protected domain is created within embedded processor's data storage address space. Each module has its own protective domain storing its status. Modules are limited to write memory out of their domains as the machine runs. A memory map checker is essential for software component access controls. Systems can be written within their own domain only. Limited memory does not allow the sequential division of address space into many domains. Instead, the microcontroller's address space is subdivided into blocks of same size. Memory map includes access to each block of address space and two types of information. The first is ownership information for each block of memory, and the second codes memory layout information. Memory protection in embedded OS kernels. Based on the three abstractions, OS is developed for embedded kernel OS. The first one is process as core execution unit. The second applies to files that have multiple I/O operations in it. The last one is sockets that are available via a socket interface as implementation of Internet protocols. All these three abstractions provide a kernel exported API. Among CPU architecture, the design is portable and provides page-level security with MMU hardware. The key concept is to use page-based memory protection to prevent one process from accessing other different processes into the memory area. It also prevents user access to kernel memory from being read. The virtual address is mapped to a physical address, allowing all operations with the same logical address and physical address assigned to them. As for memory management, a one-to-one memory mapping significantly simplifies the memory management subsystem design. In fact, the protection mechanism is domain-based and consists of memory pages mapped with a set of page tables. In addition, kernel-related memory pages are combined into a set called kernel tab. All domains are mapped with kernel map. Now I will discuss about another embedded OS memory protection that is especially done for Pico Blaze soft controller, and this is one of the latest work of the researchers. This work focuses on memory protection function based on real-time operating system on Pico Blaze soft controller. The research investigates how existing embedded operating systems achieve memory protection and applies the Pico Blaze processor to test such function. In addition, the researcher designed hardware and software perspectives to protect the memory. The hardware is designed to achieve additional memory protection units, while the software is designing assembling code which enables CPU to execute similar instructions. This is an Pico Blaze OS model in figure 3. With regards to design requirements, because the system is a small embedded operating system and certain protection schemes are not worthy of being applied in the system, current design is deemed in all always to be the best option for such system. The researchers, however, struggled to achieve complete functions for the operating system. The research has only innovated in the hardware dimension. Unfortunately, however, the research was not done as it sits from the whole software system. Full OS functionality in the software section needs to be supplemented. Here, I will stop my discussion and I would like to invite Helaluddin to discuss our further works. Thank you.
Thanks, Moshrefa, Sultana, Chaity, for giving me the opportunity to present rest of the part. So I'm going to take it from here. Sorry for the inconvenience. So in this section, I'm going to discuss about some memory protection approach that developed by the researchers so far. First of all, I'm going to discuss about an approach that called SOFME, and it's the full form of software-based memory encryption protection approach. What SOFME does is simple. It's utilize the on-chip memory areas protect confidentiality area to protect confidentiality and integrity of stored data on the off-chip memory, and it ensures significant improvement in the security with no significant increase of overhead. Nowadays, embedded system is an ubiquitous thing. With the vast improvement of Internet of Things, the demand in the security phase of real-time operating system is increased significantly. ARM proposed the trust zone to improve security of data in real-time operating system and applications. Yet, trust zone is vulnerable to resist effective physical attacks. To address this problem, the authors of this paper, SoftMe, proposed and implement a viable solution, software, and it's a software-based solution. In this section, I'm going to talk about some basic architecture of SoftMe. With the improvement of technology, attackers become much more smart and they design various attack methods for real-time operating system. Among them, some popular attack method is cold boot attacks, bus monitoring attack, DMA attack, and etc. Sopni proposed a software-based protection approach to resist those attacks. In their system architecture, they utilize Trust Zones technologies secure vault to allocate on-chip memory space which can resist cold boot attack in the operating system. And the hardware resource of Trust Zone divided into two worlds, one called secure world and another called normal world. And the secure world is also divided into two small portions called on-chip memory space and other is called DRAM. To ensure secure communication between two worlds, the author allocate a small piece of shared memory. You can see from the figure here, and they design a task scheduler and a memory protection engine (MME) that my partner talked before earlier slide and discuss some properties about memory uh, protection unit. In this small piece of memory, they allocate they implement a memory protection engine that's a software based approach, and the responsibility of the memory management engine is it can schedule multiple tasks and maintain fair execution at all the time. And the work of memory protection engine is encrypt and decrypt tasks during reading data from on-chip memory. MP used APIs, which is Neutron standard, those capable of real-time multitasking. And the fundamental role of the memory protection engine is to process sensitive data on DRAM and write back the task data to DRAM after execution. Finally, SoftMe protects trusted task against physical attack. It's a software-driven approach, and memory protection mechanism is stored in the on-chip memories shared area to protect confidentiality and integrity of the task stored on the on-chip memory in the OS. In the experimental result analysis phase, it shows satisfactory result. With single core operating system, it may not work perfectly because encryption and decryption takes a lot of time uh, with only one core. So the overhead will be much more large for single core OS. And as IoT area is very broad, sometimes IoT things and embedded systems things deal with various tiny elements which uh, majority of which have like little equipment. They are basically equipped with a single core system, so that will be very problematic. So Those are the some drawbacks of soft MIP. Now I'm going to talk about another approach called Dynam P, which is full form of Dynamic Policy Driven Memory Protection. It's ensure data confidentiality with minimum overhead. To ensure confidentiality of sensitive data, it defines some policies in scratchpad memory. Nowadays, data confidentiality is really important because of its widely use. For example, lots of sensitive data we're using in mobile banking, social networking, and various other platforms. So to make sure data integrity and confidentiality against unreliable access, a memory encryption uh, approach is must. Many proposed system can many proposed system are suffer from overhead of encryption and decryption operation. To address this problem, authors propose policy-driven scratchpad memory allocation methodology. So now we are going to talk about the design of DynaPOM. The main design goal of DynaPOM is to minimize the cost of data transfer from or to off-chip and encrypt and decrypt of sensitive data. To achieve those benefits, uh, DynaPOM utilize scratchpad memories which which can be easily controlled by software, and it can reduce cost of memory access overhead. Some simple SMP policy can outperform the performance of cache. There are three policies in this approach. Uh, they named him they gave him three different names. First name is sensitivity first. Second policy is access first. And the third policy is they called hybrid. So what are their responsibilities? So minimizing the cost of encryption decryption operation due to reduce the off-chip memory's access is called sensitivity first. And restrict data map to off-chip memory area via selective encryption decryption is called access first. Switch between sensitive data and non-sensitive data referred to as hybrid. Their proposed method, they reduce the cost of encryption and decryption by keeping sensitive data in SPM as long as possible. Also reduce the data transfer cost by taking high access frequency data from SPM. To determine their approaches efficiency, they compare the performance of their SMP allocation evacuation method with the conventional SPM allocation. Overall, their proposed encryption decryption approach improves the memory latency by up to 42.82%. Maybe it will not work smoothly with the multi-core system. Now I'm going to discuss about another memory protection approach is called MIP, and its the full form of this is Memory Integrity Protection Method. It's an ARM based platform that defends against security threats include kernel data attacks and direct memory access attacks. It utilizes touchstone technique to create isolated execution environment. Moreover, it uses a formal method called B for providing integrity protection strategy. To differ the execution within secure world and normal world, touchstone relies on NSBIT. where MIP provides a secure monitor mode that manages the switches between a secure and non-secure world. Entry in the normal world is strictly monitored by the controller mode, whereas entry in secure world is little more flexible. For maintaining the integrity, unreliable operating systems kernel code is not allowed to execute in the target device until it has authorization from integrity verification program. So the authors proposed and implement MIP, which is hardware assist architecture for for practical memory protection. They evaluated result in terms of both load time and overhead. The automatic proof rate of machine using B method is about 78.32%. From the result analysis, it can be said that it will support potential application on trust zone enabled device. So to wrap up, uh, in our broad presentation, we have discussed different type of memory protection for real-time operating system that have been developed so far. Also, what is real-time operating system, what is memory protection is unit, what is memory management unit, and etc. Among all those memory protection techniques, some are targeted for single core, some are targeted for multi-core. Some provide great memory protection for real-time operating system, but struggle with overhead. Some does not struggle with overhead, but not suitable for multi-core or single-core system, vice versa. In future, when we will uh, build memory protection system, then we need to consider both performance and low overhead, also support for both multi-core and single core system. We need all of these things in our head before designing any memory protection unit for real-time operating system. So that's it, and those are our references. And so so that's the end of our presentation. Thanks for being with us, and if you guys have any question, please feel free to ask. Thank you.